Hello everyone, welcome to another video in the series designed for protection and control engineers. Today we are going to focus on technical math which I feel like every protection and control engineer should know about. So now the question comes into the mind, why maths? See, the skills that you will learn in this video are absolutely necessary for you to fully understand what you are doing when you're performing any number of ordinary tasks. For example, let's say you are in field and you want to do a load check, or you want to calculate a scaling factor, or let's say you're working on Kirchhoff's law, Ohm's law. So you need to fully grasp the concept of maths. This will even become more important as we move more and more into microprocessor based relays and instruments, where you'll actually realize that the basic knowledge of trigonometry and Boolean algebra is crucial to understand these concepts. So that's why I feel like every PNC engineer should have a basic knowledge of maths, which is I'm going to discuss in this video. So these are the topics that we'll go through in this video. The first will be algebra background. Second, we'll discuss very basic concepts about trigonometry. Then I'll give you an introduction on vectors and phases. And finally, we'll conclude this video with learning a little bit about Boolean algebra. So now we will look at the basic rules to follow when we are doing addition, subtraction, multiplication and division of positive and negative numbers. So the first rule is that any number on the right hand side of the number line is positive. So what is a number line? So let's say you have a line like this. So any number to the right of 0 will be positive. So, and any number to the left of the 0, which is the next statement, will be negative. So in addition, whenever you are adding, like let's say you have plus 5 with the same sign, which is like plus 2, the answer will always be positive. But let's say you have like plus 5 and you're adding a negative number, let's say like minus 2, the answer will still be positive. So whenever this number over here is smaller than this number, the answer will be positive if this number is positive. Now for subtraction, let's say you have same signs, you have minus 5 and minus 3, the answer will always be negative. So if the both numbers are like negative, both numbers are towards the left side of this, so the answer will be negative. So number will keep getting pushed on this line further and further. Simple. Now with multiplication and division, again it's simple. So the basic rules are as follows. So whenever you have like same signs, then the answer will always be positive. So for example, let's say you have like plus 10 divided by plus 5. Answer is 2, which is plus. If you have 10 multiplied by 5, which is like 50, the answer is positive. Same goes with if both the signs are negative. Let's say you have minus 10 divided by minus 5, the answer will still be positive, which is 2. However, in multiplication and division, if the signs are different, then the result will always be negative. So and this number can be very big. In addition, we saw that if like this number is bigger than, let's say like this number, then the answer will be positive. In division and multiplication, that's not possible. So let's say you have like minus 100 divided by 2, the answer will be negative. But let's say you have plus 100 divided by minus 2, the answer will still be negative. So it does not matter if the number is bigger or smaller. If the signs are opposite, the answer will always be negative. Okay. So now we'll look at some basic concepts of trigonometry. So see, when you will be working with vectors and phasors, it is necessary to have a basic understanding of some of the fundamentals of trigonometry. I would say like plane trigonometry, because plane trigonometry deals with like 2 dimensions, and this is what we are going to deal over here. There is no 3D stuff. And simply in mathematical terms, trigonometric functions are basically like ratios which actually depend on angle. So these are some of the identities, like sine square plus cos square is equal to 1, and you need not memorize them, just like a basic understanding is fine, and we are going to actually prove this one. So before that, let's understand what a Cartesian coordinate plane is, or simply a coordinate plane. I'm pretty sure you all have seen this coordinate plane in geometry. So over here you have like 0, and then this is the x-axis, this is the y-axis, and that's why it's called like 2D, because two dimensions, x and y. So again, anything on the right of the 0 or anything over here is positive. Anything over here will be negative. So it's called coordinate plane because like you have like this coordinate. So let's say like this and this. So what is the coordinate over here? 3, 3. So we write the x coordinate first and then we write the y coordinate. So it's a coordinate plane. Okay. Why it is important? Because let's understand it now. So what I did was, if you remember, like we had this coordinate plane like this, we had 1, 2, and like x plane and y plane, 1, 2. I just magnified this over here and made this a unit circle. So what is a unit circle? You actually have a distance from this point 0 to this much point is actually 1. So now if you see, the angle between this x axis and y axis is 90, 90, 90, 90. So basically 90 multiplied by 4, which is 360. So this basically is like a circle. That's why this circle is formed over here. And it's called a unit circle because the distance from origin to this point is 1. Okay. Now let's say I have a line like this. This is a radius. Its value will be 1. Any point from this origin on this circle will always be 1 because that's the radius. Okay. So let me like draw like this and like this. Okay. So let's zoom it out over here. So basically you have a circle going like this. So let's say you have a theta. This is just forming an angle, right? This angle will be 90. And let's say I have 2 points over here. I am calling them cosine and sine. Okay. So what is sine now? Or sine of theta? So sine of theta will be always opposite upon hypotenuse. This is the hypotenuse. This is opposite. This is called adjacent because it's basically near to this theta. Okay. What will be cos theta? It's adjacent upon hypotenuse. And tan theta or tangent theta is basically sine theta upon cos theta. So it's basically opposite upon adjacent. Now if you remember, we had this identity over here, sine square theta plus cos square theta is equal to 1. You can actually prove it over here. So if you have calculators nearby, you will actually see that if you multiply, like what will be sine of let's take this angle as or not even angle. Let's say that this distance is over here is 0.65. Yeah, 0.65 should be fine. So sine of theta will be 0.65, which is this distance, okay, upon hypotenuse, which is 1. Cos theta is 0.76, okay, divided by 1. Okay. Now if you use your calculator and if you see like 0.65 square plus 0.76 square, that will come approximately equal to 1. You can just do it on your calculator. And this is where like this identity states true. Sine square theta plus cos square theta is equal to 1. Now another reason, as I mentioned in my introduction, like when you're looking at a distance relay, so a distance relay would have the characteristics like this. And it is very important at that time when you'll understand like when the relay would trip or when the microprocessor distance relay would trip and when it will not. Because see, the name states distance relay, right? So it's going to calculate a distance, and this will be one of the characteristics of that relay. So that's why I wanted to introduce this very basic concept to you. Again, when we'll go into distance relay, we'll definitely go much deeper. But for now, just understand this basic thing. So now let's look at introduction to vectors. So see, as power system engineers, you will see phasors a lot of time. Okay. But phasors are actually particular type of vectors and they can be manipulated the same way as vectors. So it is first necessary to understand like what vectors are. Because if you understand vectors properly, then understanding phasors is easy. So as I mentioned, like this is why I'm giving this introduction to vectors, because again, they can be manipulated the same way as phasors. So vectors actually have a direction. So we have like scalars and vectors. So what is a scalar? A scalar is a quantity which will only have a magnitude. So let's say like I drink 3 liters of water every day. So this is just a volume, right? Like I drink 3 liters. There is no direction. Now if I say like there is a train that is going from let's say north to south at 100 kilometers per hour. So now I'm actually giving a direction as well. So that is actually known as vector. So you see like a vector has a direction. And like I kept this image over here because like in physics this is how they actually teach you. Like there is a force, and you have a block like this. So there is a force that is being applied of magnitude like 10 and at an angle of 15 degree. So vectors, this is vectors. So now we come to rectangular and polar coordinates. So see, like again, if you remember in just a few minutes ago, we saw this Cartesian plane. So basically, like there are actually two ways to describe a point on the surface. So like for example, this is the coordinate of this point is 1 comma 1. Why? Because this is 1, this is 1. And so basically what a rectangular coordinates will do is they will define a distance from the x axis and the y axis. So for example 1 comma 1, the point over here is minus 3 and 4. Why minus 3 and 4? Because first is x, remember, and the next is y. So this one, and it's positive, so it should be here. So the coordinates of this point are minus 3 and 4. Now vectors are actually defined using real and imaginary notation. So like if you have a rectangular coordinate, you can say like minus 3 and 4. But in vector definition, it's going to be like minus 3 plus j multiplied by 4. You can use j, you can use like even I, doesn't matter. But then this part refers to the complex part and this part refers to the real part. This is important, and if you have watched my second video, we actually saw like active and reactive power. So like active power is real, reactive power is imaginary. So this is that vector notation. Yeah, so like as I mentioned, 1 comma 1 would be represented as 1 plus j into I. Now we have the polar coordinates. So see, like just as we describe a point on a plane, we also describe a vector, right? So like you have these angles over here. So what will be the coordinate of this point in polar form? So basically, like let's say this distance is 1 and it is forming certain angle. Let's say like 45 degree. So then the coordinate of this point in polar form actually becomes like 1.4 angle 45 degree. Okay. Yeah, pretty, you can actually, convert from polar to rectangular, which we'll look now, or rectangular to polar. Yeah, so basically it's actually a location of a point from a straight line and at an angle. So let me, so what is the coordinate of this point? So this distance, and it is at what angle? This is what a polar represents. What a rectangular coordinate shows, where they are actually intersecting. So this is rectangular, whereas polar shows like this distance, this. So now you understand. So let's say you have a triangle like this. Okay, so let's say that this is 5, this is 0.5. So the rectangular coordinate is 5 comma 5. Okay, let's say this angle is maybe 30, this is 90, this will be 60. So what will be the coordinate in polar form? So you need to find this distance. This is hypotenuse, so we can use Pythagoras theorem. So 5 square plus 5 square, and we take a square root of that, so we'll get this hypotenuse value. And the angle, that will be 30. So 25 you get like 50, and the square root of this would be 5 root 5. So root 5 is like maybe 2.1 multiplied by 5. I'm just taking it like 10. So like 10 angle 30 is your polar coordinate over here, and the rectangular coordinate is 5 comma 5. Simple. Next thing is, so the way we measure angles, if you see, I measured the angle like this and told you it's 45 degrees. So this is counterclockwise. Okay, why counterclockwise? Because let's say you have your like watch like this, so I'm going against the watch, so those angles are treated as positive. If I'm going into the direction of clock, like 12, 1, 2, 3, your clock moves like this, right? It's at 1 o'clock, then 2 o'clock, and then 3 o'clock. So if I go like this in clockwise direction, it will be negative. So let's say I have my A and a point B. So this angle, because I am going in counterclockwise direction, it will be plus 30. But let's say I have like this C, and if I want to measure this angle, now I am going in the direction of clock, so this angle will be negative. Let's say like minus 210. Okay. Also remember that rectangular coordinates can be added with rectangular coordinates. Polar coordinates can be added with polar coordinates. Let me elaborate on this thing. So let's say you have like, for example, one angle 45. You cannot add this with, this is the rectangular coordinate, this is the polar coordinate. You cannot add this. That is not allowed. Either you need to convert this polar into the rectangular form, or you need to convert this rectangular into the polar form. Now we have engineering calculators that can actually like do it, convert from rectangular to polar and polar to rectangular. So I will not go into details as to like how to do it. But remember, polar can be added with polar, rectangular can be added with rectangular. Okay. So now coming to introduction to phasors. See, as a protection and control engineer, phasors are very important. So whenever you will be looking at the PNC drawings for substation, for transformers, voltage transformers, current transformers, you will always see phasors. So it's very important to understand the basic idea behind phasors. And I'll tell you from my personal experience, when I started my career as a protection and control engineer, this is one thing where I used to make a lot of mistakes. And if if you don't understand phasors correctly, this could actually result in malfunction of the relays itself. And in upcoming lectures we'll see like how that can happen. So but for now I'll just say like, please pay attention and understand basics about phasor. Okay, so see, a phasor is basically similar to a vector, but a phasor will rotate about an origin. So what does this statement mean? So like, if you remember, we had a vector like this. Okay, so what is phasor? A phasor will keep on rotating. So let's say like right now it's at 30 degree, another moment it will be at 60 degree, another moment maybe 110 degree. So it will keep on rotating. It is not static like a vector. It will keep on rotating. That's why like you must have seen these symbols for phasors. This is actually a 3-phase phasor, but just for representation purpose. Second thing, so any phasor will be a snapshot of its given time. Yeah, because see it is rotating continuously, right? It's not static like a vector. As I mentioned, like it's rotating. So whenever you see a phasor, like let's say you see a 3-phase phasor, that is actually a snapshot of just that given time, because it's going to quickly change itself, something like this, again something like this. It's going to keep on changing. So whenever we show any phasors on the drawing, they're just snapshot of that given time. Okay. Yeah. So again, remember, angles going against the clock are measured positive, and angles going in the direction of clock are measured negative. That's how we look at phasors. So basically, let's say you have a phasor like this. It's continuously rotating. So the number of times it rotates about this point per second is actually called frequency. I'll repeat it. The number of times this phasor is rotating per second is actually called as frequency. So like the frequency in India is 50 Hertz. So what does that mean? So that means like this phasor has rotated about this point 50 times in 1 second. That's why the frequency is 50 Hertz. Frequency is measured in Hertz. I'm pretty sure you know this. The frequency in US is 60 Hertz. So what does that mean? So that means like this point has rotated 60 times in 1 second. And that's why the frequency is 60 Hertz. Okay. Again, phasors are valid only for AC, because AC is actually, like pulsating, right? So the phasors keep on rotating. Why not for DC? Because they are not rotating. DC is like this. So a phasor for a DC is actually a vector because it's static. For AC, it's actually a phasor. That's why these are valid only for AC and not for DC. Okay. Now coming to the concept of leading and lagging phasors. So see, before we even start the discussion of what is a leading and a lagging phasor, we need to understand like 3 things. First of all, there need to be 2 phasor with which we can compare, right? What does this point mean? So let's say like I have a phasor A over here. Now I have to compare it with some other phasor, right? I cannot, how can I say like this phasor is going ahead or this phasor is not going ahead? So it has to be compared with something. So that is why we need actually 2 phasors. That's what this line mentions. So we have like phasor A and phasor B. Second thing is the phasor should move in same direction. Yeah. So let's say like A phasor is moving like this and B phasor is moving like this. No, you cannot compare them. It's basically telling like, let's say this is the start line and this is the end line. Okay. So one player starts from here, like player A is running like this and player B is running like this. How will you compare like who's running faster? You cannot, right? They have to run in same direction. Or who will be the winner? We don't know. They have to run in the same direction. So that's why the phasor should move in same direction. The third thing is they should have same frequency. Again, like as I mentioned, the number of times this phasor moves per second is actually called as frequency. So they should have same frequency. Like for example, let's say this frequency is 50 Hertz. So this has moved like 50 times in 1 second. This also needs to be 50 Hertz. It cannot be 60 because then it starts moving faster than this. So this is the important thing. Okay. So in this case, if you see like phasor A and like 23 degree, phasor B. Okay. So phasor A is actually leading phasor B by 23 degrees. Why? Because let's say you are over here, standing over here. Which phasor will cross first? The A phasor will cross first and then the phasor B will cross. So that's why A is leading B. Okay, by 23 degrees. That is the difference of angle between them. B is lagging phasor A. Why? Because A will come first and then B will come. So B is actually lagging A. So this is the concept of leading and lagging phasors. You will see this concept of leading and lagging phasors in resistive and capacitive and inductive circuits, which I think I have a video explaining that, but this should help you understand that as well. Okay. So now let's look at balanced three-phase phasor. So what is a balanced three-phase phasor? Okay. Now we see over here. Now tell me what phase notation do you think is correct over here? Or what is the phase sequence actually? Is it A, B, C or A, C, B? Assuming like, this is the reference vector. So if they are moving like this in this direction, what should be the phase sequence? This or this? See, this is the common mistake that happens in the beginning when they say draw a ABC phasor, a balance, let's say a balance ABC phasor. What generally people do, they take A as a reference, they make this B and they make this C. So they think it's going to rotate like this. This is wrong. This is actually ACB. So this over here is actually ABC. Why? Let's say you are standing over here. Okay. The first phasor that will hit you is A because this is the reference phasor. Then the next phasor that you will see is B. And then the next phasor that you will see is C. So one of the properties of this balanced phasor is that they have same magnitude. Like if you measure this distance, this will be 1, this will be 1, this will be 1. Plus they are separated by same angle. So this angle is 120 degree, this is 120 degree, this is 120 degree. Okay. A balanced set of phasor is such that the vector sum of them will be 0. So let's say you have like VA is equal to 120. I'm just sorry, not degree, I'm just taking length as 120 and let's say the angle is 0 because this is the reference angle. The voltage of B would be, let's say, 120. What would be the angle? If you measure it counterclockwise, it's 120 plus 120 because we are measuring from this reference angle over here. So I'm measuring this angle. So it's 240. C will be what? 120 angle 120. Now if you use your calculator actually and you add VA plus VB plus VC, you will see that you will actually get an answer as 0 angle 0. You can try on your calculator. So this is the most important property of a balanced phasor set, that the vector sum of the set is equal to 0. So now let's look at unbalanced phasor. So what is an unbalanced three-phase phasor? So now you see a diagram over here. So the first thing that you will notice is that the currents are actually leading or lagging voltage. They're actually lagging the voltage. Why? Because again, see, stand over here. Let's say it's rotating like this. Okay, positive. Okay, because it's rotating counterclockwise direction. First thing you will see is voltage A, and then you will see the current. So the currents are actually lagging the voltage, or you can say that voltage is actually leading the current. Okay. Second thing is, like, these are two sets of phasors that are not of the same quantity. Okay, this is important. This is the voltage phasor. So if I like separate them, this is voltage phasor and this is the current phasor. So they are two different sets of phasors. Now let's say you have like four. I'm actually using these values from the book. Okay, and let's say the value of current is 4 angle from the book. So now when you actually add this, you can try using a calculator. You'll actually get the I sum, which is IA plus IB plus IC. It's going to come around to be 0.21 angle 343. Very important. So you see it's not 0. So they are not balanced, they are unbalanced. So this 0.21 is actually called as the ground current. Again, remember this is called as ground current, and this is what is seen by the ground relay. Now you might hear terms, like the neutral current, or like ground current due to balance, or residual current. So this is that ground current, and this can actually cause the ground relay to trip, because it will realize, oh, there is a fault. Because if it's not a fault, then it's a balanced system. There should be the vector sum should be 0. But if there is a fault, then there is a disturbance in current. Let's say there is a fault in phase A. So what happens? This will increase, right? Whenever there is a fault, voltage would decrease. So let's say this increased. So the sum of this is not now 0. So this will see the ground current, the ground relay will see this, and the ground relay will trip. So basically, we try to make it as close as possible to 0, so that like this sum is, I mean, it won't be entirely 0, but very close to 0. And that's why we have some thresholds on setting the ground relays. Okay, I hope you understood this concept. So now we come to the final topic, which is Boolean algebra. Again, Boolean algebra is very important, because whenever you'll see any microprocessor relays, the logic diagram and the logic of it is actually written in this Boolean form. You will see, like a logic diagram of a microprocessor relays, where you will see AND gate, OR gate, NAND gate. There will be bunch of gates. So please pay attention to this topic. And even when, like when we'll see the inside logic of a relay, like trip equations, and you will see that in trip equations, or like any condition that needs to be fulfilled when the relay should trip or not, those all will be written in Boolean algebra. So it's very important, please understand this. Okay, so Boolean algebra, like a bit would represent if a condition is true, which is like 1, and if the condition is false, which is 0. So when it is used in this manner, it is actually called as Boolean. So there is like a truth table. I'm sure you might have seen a truth table, but again, we'll look into it. So as I mentioned, this is very, very important for understanding microprocessor relays. And these are the different gates that we will see, like AND gate, OR gate, NAND gate, XOR gate, NOR gate, and NOT gates. Okay. So the first gate, that is AND gate. So this is the truth table for AND gate, and this is the symbol. Any microprocessor logical diagram would actually have this symbol. So you need to know like what a AND gate looks like, what a NOR gate looks like. They will basically have like this symbols and bunch of something coming like this, and then forming a logic. So I mean, it's not going to be this simple, but then if you know like what function this gate performs and what function this gate performs, it becomes very easy to decipher any microprocessor relays. So a AND gate is actually composed of 2 or more inputs, like 2 inputs over here just for simplicity, and there will be 1 output. So from the truth table, you can see a AND gate is actually a logical multiplication gate. So whenever you have an input false, which is 0, a false input 0, so 0 multiplied by 0, 0, 0 multiplied by 1, 0, 1 multiplied by 0, 0, 1 multiplied by 1 is 1. So that's why a AND gate is actually called as X is equal to A, B. So for a AND gate to have an output of positive, or let's say, sorry, not positive, like true, which is 1, both the input should be true. If one of the input is false, the output of the AND gate is false. Understood? Yeah. So as I mentioned, like X is equal to A multiplied by B. The next is OR gate. Again, this is the truth table for OR gate. This is the symbol. See, it's different than AND gate. AND gate had a symbol like this. This is the OR gate. Okay, this is the AND gate. So AND gate actually performs logical addition. I'm sorry, the OR gate actually performs logical addition. A AND gate would perform a logical multiplication. A OR gate would perform a logical addition. So again, 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 1. It's not 2. This is the Boolean logic. Okay. So yeah, you see, the output would be high when one of the input is high. The output would be low only if both the inputs are low. The or output would be false. So now look at NAND gate. So a NAND gate is actually a combination of a AND gate and a NOT gate. So if we connect the output of a AND gate to the input of a NOT gate, then we'll get this NAND gate. And it's a very popular actually logic element because it may be used for any universal function. So if you remember, like as I mentioned, AND gate is like this. A NOT gate, which we'll discuss after this slide, is like this. So when you connect these together, this is what a NAND gate is. And let me erase this so you can see the truth table. So it's like, as I mentioned, it's called negated AND gate. So this sign over here actually dictates that. So what is negated? So A multiplied by B, if this would have been an AND gate, the answer would have been 0. But what a negated AND gate does, it does the opposite of what the AND gate will do. So the answer would actually become 1. 0 multiplied by 1, if AND gate, it was 0. So then opposite of that is 1. Similarly over here. Now in AND gate this is 1. So this NAND gate will do opposite of that. So it will be 0. Okay. NOR gate. So a NOR gate is like not OR gate. Basically this N over here stands for not OR gate. So this is the truth table for that. Again, if you see, like this symbol over here says that we will do opposite of what is mentioned over here. So if this would have been a OR gate, 0 plus 0 would have been 0. So what a NOR gate does, opposite of that, which is 1. 0 plus 1 is, according to OR gate, it's actually 1. So not OR gate will be 0. 1 plus 0, again according to OR gate, is 1. Opposite of that is 0. 1 plus 1 according to OR gate is 1. So not OR gate, NOR gate is 0. Simple. Again, this symbol is important. And this is the symbol that I told you, like for NAND gate. If you remember, like and you know. So NOT gate. See, a NOT gate will basically perform a inversion. So whatever is positive will be negative. So this is just like, it's very simple. Again, this symbol denotes that. So you have like input 0, which is false. You get opposite of that, which is high. Input is high, the output is. So now let's look at exclusive OR and NOR gate. Okay. So this is the symbol for exclusive OR, the truth tables, and exclusive NOR. So XOR gate, it's actually called as like exclusive gate. So it's actually digital logic gate that will give a true high, or like a true basically output when the inputs are actually odd. So what do I mean by when I say odd? So basically, if either one of the input is high, then an exclusive OR gate will actually produce a output high. So like when one of the input is odd or high, so in this case you see like this is high, so the output is high. If they are of same, like if both the inputs are same, they are both false and both true, then the output will actually be false. So exclusive gate, it's actually like a important gate because it is actually used as an inequality detector. And if whenever it will see an inequality, it's gonna go high. So it's actually a important gate. Now if you look at exclusive NOR gate over here, so you see a bubble over here. Yeah, this actually denotes like something n, like a something opposite is gonna happen. So you see this bar over here. So what this gate actually does is this actually does opposite of what an exclusive OR gate does. So for an exclusive OR gate, as I mentioned, if both the inputs are same, like even inputs, it results in 0. This will just flip it. It's actually make it high. So 1. So you see over here, for exclusive OR gate, it was high. So this is 0, 0. For exclusive OR gate, this was false. So this is actually true. So this is actually a truth table about exclusive NOR gate. So again, like there are a lot of applications of these gates. You can, like, exclusive OR gate can be used for a half or a full adder. I don't want to go into much more details in power electronics, but yeah, I mean, if you understand this basic truth table about this, then again, as I mentioned, it's easy to actually decipher any microprocessor relays. Now there are some Boolean algebra rules. Again, like this basically states that whenever a high is added with a low, you get a result high. A plus 1, again the result is actually 1, not A. Okay. A multiplied by 0, this is AND 0. A multiplied by 1, you get A. A plus A, high plus high, high. A plus this not A, you get 1. See, these are some important tools. I'm just reading from this table. A multiplied by A, it's not A square as we saw in the first slide of algebra, exponents. This is A as per Boolean algebra. A multiplied by not A, 0, false. Double A, so basically what it's saying is, like, this is actually not equal to A, right? This will turn opposite of what A is. So if I put a double bar over here, this will actually give me A. So for example, A is 1. So A bar is 0. I put a double bar over it. So opposite of A bar, which is again 1. So this is equal to this, right? So A double bar is equal to A. A plus AB is A. A plus not A, B is B, because this will be 0 then, right? Why? If A is 1, A bar is 0. This is distributive principle. A plus B multiplied by A plus C is A plus BC. Okay. So this is just an example that I took. So just to reinforce the concept. So if you see over here, like whenever there is an input that is 0 0 0, so let's say like 0 0 0. So what is this gate? This is NOT gate. This is AND gate. So input 0, output will be 1. It flips it, 1 0. So now 0 1 1. AND gate needs to have all conditions as true in order to give output true. So 0. So your output is 0. So you see like how using NOT gate and this is constructed, and you can just follow like all this over here from this. So this is how different gates are actually used to perform particular operation. And you will see like multiple gates like this in microprocessor relays when they are performing different functions. They might even be separated. So you might have like a different gate over here, and you might be getting a like input to this from this, or maybe something like this. Output of this might become an input to this, and they will perform different functions of closing, tripping, which we'll see later. So this is just an example of this. So with this, I would like to conclude this technical math session. I hope you actually found it useful and you were able to, like learn something from it. If you already know this, I hope that you are able to brush your concepts up. And for those, like who are new to this Boolean algebra or trigonometry or other concepts, I hope that like you found this video useful. So I would request like if you could comment about how did you like this video, what did you like about it, or like if there are any shortcomings, and what are the topics you might want to see. And if you could like and subscribe my channel, so that like I'll keep putting more videos out for protection and control engineers who would be working as in substations or as substation design engineers. So yeah, thank you everyone, and yeah, have a nice day. Bye.